So this is how the process deals with mallocs. Let us look at how the process deals with freeing space. Okay, so you call free, or you free 10 bytes. Okay, so the used part, the middle part, is going now to be freed, which basically will change the linked list from basically from basically two nodes to three nodes. So basically, the first one is basically starts at address 10, and it has a length of 10, which is the one that you just freed right now. The second one is the address 0, because when you insert to the linked list, you inserted the new free space to the head of the list, right? And then the next one is basically the first chunk that was free, which is address 0, length of 10, and then the second chunk is address 20 and length of 10. So now you have three adjacent free areas, right? So what you want is to be able to basically combine all the adjacent free memory, and you can do that. Okay, so you go basically from here to here, where you basically have a whole lot of free memory from 0 to 30. Okay, and you can do that by basically every now and then going through your linked list and seeing and sorting the linked list out, and making sure that your linked list is basically that there are no adjacent chunks that are free, that have not been freed. Okay, let us look at a much more complex example, which uses mmap that we just talked about. So mmap is a way to create a new heap. It's one of the ways. It's not the only way. It's one of the ways. And as I was just saying, that when you do segmentation, you can have a heap that has common that is shared between multiple processes. So mmap allows you to basically create a chunk of memory. In this case, for example, let's look at the code that starts from node t pointer head equals mmap. It starts basically, it has 4096 bytes, so 4 kilobytes, which is a small one. And then you basically say that it's protected on read, protected on write, and this is a private memory. You can actually, using these different flags, you can have, for example, the map to be shared. And I think there is an example in the book where they show shared memory, for example. And also it says, although it's shared, is it shared for reads only, or is it read write shared, and so on. So mmap is a very, very efficient call when it comes to you trying to build a heap that can be shared between multiple processes at the same time. You also create sort of a linked list entry, and that is basically your node underscore t. Okay, this is your sort of linked list that your operating system is going to use, and in general your memory manager is going to use. And this is actually highly relevant to the to the assignment that has been posted today on Moodle by Colin, in which you'll basically do the sort of management and memory manager. You'll build it yourselves. So there's more information on mmap in the book, and there is much more information on the syscall description that you can find online. When you create a new heap using mmap, you have to note that, well, you create the heap, so you create the space, and that space has the size of 4088. Okay, you actually created it with the size of 4096. But the reason that you have 4088 for the size is that there is a size for the metadata, for the description of your node. So basically, when you create the mmap, you create it, but you still need to store some metadata on this heap that you just created. And that metadata is basically has 8 bytes basically, which is basically the header field for your heap. Okay, it contains also where, for example, things such as the size of the heap and where's the next free space. So you created this, you have all of this as free space, the rest of the 4 KBs, only the size stored and what is the next, because this is linked list, so what is the next pointer basically, which are the 2 values that you have here in the node T basically. Okay, so now you have that. Suppose that you want to allocate 100 bytes, okay, using malloc 100. So now you update your memory allocation such that the first 100 bytes are allocated using malloc, but you and you add like, okay, now I have size of 100. This chunk starts with the size of 100, okay, and the magic, which is basically virtual sort of your virtual address, magic number, and this is the rest of the 100 bytes. So you will actually not get the 100 bytes allocation, but you'll actually get 90. You'll get 92 bytes allocation if the size is 4 bytes and the magic is 4 bytes. Okay, so you get 92 allocated memory. And now the head of your, so right now you had the head at the very top of your heap. Now the head moves down because you have allocated a chunk of memory. Okay, and now you have 3,980 bytes free because you just took 100 bytes out of your 4,088. Okay, and you took also 8 extra bytes to basically for metadata, and then your next is basically 0 here. Then twice more, so you add more 100 bytes and 100 bytes. You allocate 2 extra 100 byte chunks using malloc or something. Okay, so now the top of your memory has been allocated and the rest is free, right? So your heap grows downwards, right? So whatever is remaining here is the free. So you have this much amount as free. Now you call the call free, basically free 100, freeing 100 bytes of memory, and your system decides that it's going to free the middle chunk that was allocated. So now, right now, you have two segments of free data. One of them has a size of 100, and one of them has a size of 3,764. Okay, so the total amount of memory that you have free is 3,764 plus 100 bytes, which is basically 3,864 bytes. It's basically the summation of the middle part and the free chunk that is at the end of the heap. Okay, and you link. Okay, you're in the middle part. Okay, so right now you have your head is here. So the head of the linked list in the beginning started at the top of the free memory, right? I mean, because your linked list is representing your free space, but now you have an earlier address having free data, having free memory. So your head moves up there. You know that it has the size of 100, okay, and then you have a next pointer that points to the next area where you have free space, basically pointing towards the chunk of memory that is down there. Okay, and you eventually need to clean up, basically freeing the 2 other allocation. And when doing that, you would want to again join the free memory together.